to computational physics course with Python. And in this course, so just wanted to make sure also that again you can everyone can hear me, and if you can't, just let me know. Yeah, so welcome to this course, and the goal here is that there is a link which I'm just now going to share. In that link, you are going to find lots of assignment questions. And this was mainly taken from a book of Mark Newman. And this is the link which I have shared. And the idea here for this course is that these questions cover a lot of things and a lot of the basics to intermediate level stuffs related to computational physics. And we are going to go through each of these questions and doing hands-on in Python, trying to solve one question at a time. And hopefully, at least when I have created this course myself and had been TA for this course a couple of times, so I felt that this is extremely comprehensive and gives you a broad idea of what people would do in computational physics, gives you an idea of computation, and also gives you a good understanding and handle of the programming language which you will be using. So for the sake of simplicity and for the sake of this course, we will be using Python, and therefore I also expect that while you have some familiarity with Python, but it's not an absolute necessary. And if some things you do not remember about Python, then it is also a good thing that while doing this course, you will be getting more accustomed to using Python for your own work. Okay, so I think that's the major goal that we wanted to that I think I am going to have while taking this course, and I'll proceed slowly going through each of the questions and mm, go from one question at a time and give enough break in between so that there is absolutely no doubt while we proceed from the one question to the other. Doing in this way, I think is good so that it can clear all the doubts and confusion which people might have. While this also slows me down, so there are a lot of things that needs to be covered, as I have given in the course overview in the flyer. So let's see how much I can achieve in the limited amount of time, but I'll not rush through. Even if I believe that even if there are some questions which we are not able to cover, that's much better than covering everything and do not doing a good job in any one of them. So I'll take this slowly, trying to explain every questions and every answer at a time, and then we are going to proceed. And I'll also give breaks for in between for you to ask whatever doubt you might have, and also feel free to interrupt me if you think that there is something that you didn't understand or there is something that needs a repetition. I will be happy to do that. Okay, so are you able to open the link which I shared in here?
No, I cannot see any shared
So
link. Where did you share?
I shared it in the meeting chat.
Uh, but I cannot see chat here. I can see question and answer option, and but I do not find any option, a chat option here.
Oh,
In,
uh, let's see. Let me also put in a post in here.
so just now I posted a question. No link is available. In response to this link, this question, you can share the link.
Let me check. Yeah, there is a Q&A. Uh, let's see. I'm also sharing the link again in the Q&A as well. I don't know. Are you able to see it?
Yes, GitHub link, it is visible now.
Okay. Okay. Somehow there is a chat as well where I'm putting it in, but maybe it's not going there. I also that there is a meeting. Uh, this meeting also comes with a uh, page in itself. There is a channel where you can also put in questions after this sessions as well, whenever you want, if you are stuck or if you have anything, any query in general. So, are you able to access that channel while going in here with that link, or you are not able to do that?
No, I do not find any option of channel here.
Okay.
But link
So,
and
are you using the Microsoft Teams app, or you are using, are you on the web, just in the website?
so in the website, because app is not working fine in mobile too. So
I see. I see. Mm. So yeah, perhaps that's the reason. There's this channel which is where I have sent invite to people in this where they can put in. Okay, so we can figure this out later and find if there is some better alternative than this. Hmm. I can actually share my screen, then you can just get an idea of what I mean. Okay, so okay, are you able to see my screen?
yes, yes, visible.
Okay, great. So I suppose there, if you are able to join the Teams app, you will be able to join this channel. I don't know, like if it is not working on Ubuntu, maybe you can, like, just to access the channel, you can try using the Teams in your mobile. That also might work. And yeah, other than that, I'll have to look if there are any alternatives. But yeah, here you can see all the posts where I also post stuffs if there are some interesting things, or even if you have any doubts later on, here you can just post it right away in this general channel, or we can create other channels depending on if there are something any specific that comes up later on. So this is mainly the thing. Okay. And this is the repository which I was talking about. Hopefully you are able to open it. So if you go to this directory homework one, you are going to, okay, not this one. Let's go to this homework one, the PDF. So this is a PDF of the assignment questions which I was talking about. So the idea here is that we are going to go from homework one to homework two all the way up to homework seven, given there is enough time. But and for each of these PDFs, we are going to go one exercise, like one question at a time, and trying to solve these in Python. And this also covers a broad range of topics in computational physics. And this is mainly the idea that we are going to get familiarized in Python and also solving a lot of real world problems related to computational physics. Okay. So are you able to open this link, which I shared?
Yes, I can open, but then the issue is that I have background of computer science and I read physics long back. I don't remember anything. those equations. And so these questions are very difficult for me. I am here in this course because of, I mean, the purpose of refreshing my understanding in Python. So the
Okay,
was to know Python, and as such, I'm not comfortable with these questions.
I see. I see. So I would say that since this is computational physics, I wanted to like, and we are using Python. So here, this course is not about just introducing Python. This is not an introductory Python course. But what I'll try to do is I'll try to explain the physics behind each of these questions as uh, best as I can. And on the way, while solving this, there will be enough of Python. And this will be mainly, I would say, that real world problems which we are trying to solve. So I'll give a background while going through each of these questions. And while we are solving these questions, we will be using Python. So in that sense, you'll get to uh, you get yourself familiarized with Python, but the questions are mainly physics related questions. There are also actually some computer science related questions later on as well regarding image processing using Fourier transforms, but they are a little bit later, like 5 or 6, as far as I remember, in these PDFs. But those stuffs will also be there. So yeah, so broad range of things. So I would say that just have a keep an open mind and have a look of a few questions as we go through, and perhaps you will find it interesting. Is that okay?
Yeah, sure, sure. I'm interested
Okay.
in the physics as such. The only thing is that, yeah, I do not remember equations of.
Yeah, yeah, not a problem. I'll try to explain every a bit of like giving a background of each of these questions. So yeah,
Yeah, thank you so much.
okay. So this is where I will be. Okay. So I hope my screen is still visible. Yeah. So I'll be using Spider for writing my Python codes, but this is also up to you. You can use, I mean, anything you want for just writing your code in Python, and uh, getting to Spider is also, I would say, quite straightforward. So I just to get things started, let me open up, yeah, Safari for you. So if you want to get Spider, all you can do is you can install this Anaconda thing, which where you can get this. Just go to free download in here. You skip the registration, and here you'll get this Linux version or Mac or Windows wherever you are, and this comes with the Spider, and which is the IDE basically, which we will be using for mm, Python. Okay, so once your Spider is set up, you'll get something like this, where on the left we will be writing the code. On the right, you will have the run place where the code will run, and in plots tab here you are going to have see some plots whenever we make plots in here. But for the first few questions, we are not going to make any plots, so this won't be that much in use for now. Okay, and now let me save this file for now. Okay. So the first question is says that a ball which is dropped from a height h with an initial velocity 0, and so write a program that asks the user to enter the height in meters of the tower, and then calculates and prints the time it takes for the ball to hit the ground, ignoring air resistance. So this is just a simple kinematics problem. So idea here is that you have a constant acceleration due to the earth, and you just let a ball drop, and you just want to find out how much time it is needed, right? So let me see if I can also start sharing the whiteboard or something. Okay, so are you able to see the whiteboard which I shared or not?
Yeah, we can see.
Okay, okay. So this is a classic, that as I was saying, a dynamics uh, kinematics problem. So here you see that there is this uh, formula which just relates the distance traveled by a body and the constant acceleration. So this is this if your height is, let me see if your height is h, then you have h is equals to, if your initial velocity is v naught, then you have v naught times t plus, if your body is accelerating under gravity, then you have something like half times g times t square.
Uh, Excuse me, in case if you are writing something, then your screen is not visible.
Oh, is it? Okay. And there's, I think, let me just type it. That will be better. Yes. So now if you, I think you can see my screen. So let me type it in here. So if you are going to do something like a distance is, if d is your distance, so then or h is the height of the body, so h height will be height is equals to, so if you are going with some initial velocity, you will have uh, u0, right, plus yeah, times time. So if the time is, there is some time which the body travels for a while, so that you'll have some u0t plus half, so this will be 0.5 times, if your body is having some acceleration, which is gravity in here, times t square. So t in Python, your square is just 2, right? So this is generally the thing that you will have. This height is u naught, which is the initial velocity, times time plus half gt square. So now here the question says that it's starts from a zero velocity. So your velocity is 0 in here. So for that, your u naught is 0, right? Because it just dropped from the tower, and that is what the question says. So that you can then ignore the first part of it. So then if your u naught is 0, then the distance that the ball is traveling is just half times g times t square, right? So now what you are asked to find is the time. So a user will enter the height of the tower, and you are going to find out how much time it is required, right? So then we can just rearrange this problem to find time. So if you rearrange this, what you will find is your time is 2 times, your time is square root of 2 times height divided by gravity. So this is generally the formula that we will be using. So this is just for explaining. So I'll comment this out. But now what I'm going to do now, we are going to explain how we will implement this in Python. So this is the formula that we are going to use. So for finding our square root, we will be using the numpy package in Python. So import numpy as np. So instead of using, so what this as does is instead of using just numpy, we will be, and typing numpy everywhere, we will be typing np. Kind of you can think of this as an alias. So we'll be aliasing numpy with np. Okay. And then we can, to find out square root, what we can do is np.sqrt. So sqrt is a function which comes as a part of the numpy package, which does square root for you. And now we have to find, like given some height and g, the time is given like this, right? So now the question is the user is going to give you height, and then we are going to find out how much time it is required. So for that, we are going to create a function. So for that, what we will do is in Python to create a function, we use def and then give the name of the function. So the name of the function can be, say, for example, give time, right? And then we will call this height, right? So the user is going to give you height, and then it will give you some time, right? And then this thing, entire thing can go in here where we will be using height, but there is some g which needs to be used. So g is nothing but the acceleration due to gravity. Yeah, and in generally for Earth, the acceleration due to gravity is 9.8 in meters per second, right? Square. It's meters per second square. That's just for uh, having the units. And this height basically should also be in meters. So one would give a height in meters. So there is also something in Python which is completely optional, which is called type annotation. And so you can also use the, just for the sake of telling Python that, okay, what I expect is a floating point number, you can also give this something like this, which is colon float. And this also gives you float. So what this would mean is that this function give time takes in the argument height, which is of the type float, because it's a floating point number. And what this gives out as an output is also a float. But this is something optional, but I find it very useful because then when things get extremely complicated, for when you have multiple functions and you are writing a very complicated thing, then it really helps to just get an idea of what are the different variables and what are their types are. Although this is not directly enforced by Python, so this is completely optional. So I find it a good exercise that whenever you write functions, you just mention what are the different data type of each of the variables that the function takes in, and also what is the data type of the variable that functions gives out. Also to keep in mind that these optional things will give you an error if you are at a version of Python, I think, which is less than 3.5. So make sure your Python version is more than 3.5. Okay.
I query here. So
Yeah.
what if I use this annotation float here and I pass a height as something else? If I pass height is a boolean parameter, then what would happen?
Yes. So in Python, there is no such checks like this. So it will not complain anything. There will be no complaint. But what happens is when you are writing a big package, there are other stuffs where this type checking is checked, and those you can run your then program or code through those type checkers, and then that can give you like, say for example, if you're writing this function and then somewhere else in your code you are calling this function with something else, for example boolean, and if you run the code in Python, then uh, normally it will work just fine, or it will give you some result which will not make any sense. But then it becomes very difficult for you to understand what is going wrong. But there are, if I have time, I will cover, there are other uh, something called code analyzers, which can then look at all of these data types and can give you an error saying that, see, at some point you have called this function with boolean, but actually you have defined this function with float. So there is a problem where you can rectify. But directly in Python, it doesn't help because Python is just agnostic to whatever data type that you give.
Okay.
So let me call this time, and this is a return time. So this is going to return time for you. Okay. And now as a user, you can put like ask for print something, or rather you can also do something called input as well. So let's call this Mm, time taken equals to, now I'm going to use something called input. So this is not going to input something, and then I'm going to give the prompt in here. So the prompt will be enter the height in meters. Okay, and this and this is going to take an input from the user, but the input, whatever you give, comes in string. So this needs to be converted to float. So what this function is doing is it's taking height from the user, converting it to float. And this is, let's see, let's call this height from user. So this is how I get the height from the user. Now what I'm going to do is I'm going to call this function to get the time. So time taken will be give time, which will be called with this height which the user has supplied, right? And then there's a print statement that I'm going to give in here, which will just say elapsed time is, now there is something called f strings, which I find extremely useful while dealing with strings. So for f strings, you just give an f in here, and here you just then mention the variable. So you see time taken is the variable that I want to do, and let's have it till 3 decimal points, say. So 0.3f is just 3 decimal point, and this is seconds. Okay, so this just says that the time elapsed is this time taken, which will be rounded off to 3 decimal points. This means seconds, right? So let me make this thing a bit larger, because this is the place we will be using in here for now. And let's run this program. So yeah, so here it says what is the height that you have to put enter. So let's say if I give a height of 100, so the time elapsed is 4.518 seconds, right? So this is till 3 decimal places, because we have given 3 decimal places in here. So is this clear?
This is it is clear. Can you increase the font size?
Which one? Sorry, can you repeat your question once again?
Can you increase the font size of the post
Oh,
by?
yes. Yes, yeah. Let me see. Is this better?
No. I did not see anything. Can you please increase it further?
Is this better?
No, might have increased. Yes, so you are increasing the font size of the right panel, but not in the left panel wherein the code is written.
Oh, I have also increased the font size of the left panel as well that I've written the code.
No, but that is not. Yeah. Okay, but then it's okay. Yeah, it is okay now. Yeah, it's okay.
Okay, okay.
My query is regarding this formatting of the output, say, 0.3f.
Hmm.
So how to, I mean, is it the standard way of formatting the things that if I want to display the things, say, till 3 decimal places or so?
Yes, I mean, if you want to like have something rounded off to 3 decimal places, so this is pretty much the standard way of how people would nowadays do in Python. Previously, there is something called percentage stuffs, which people also used to do, but I think that this is much more straightforward in how things are done these days.
Okay.
Yeah, so but is it also clear to you like how this formatting is done, like uh, the way I put this in?
Yes, so the argument here is the time taken, which we have enclosed within the curly brackets. And
Yes.
then after the colon, we have indicated that you want the output within 3 decimal places.
Yes. And if you do not have this colon and just give something like this can also work, but it just gives you lots of decimal places. So it just gives you the raw number in itself. So for example, if you do this, you'll get something like this. So this is just
Yes.
uh, the entire thing, right?
Yes.
Yeah. And even, for example, you can also have something called the scientific notation. For that, you just give E. So for F, instead of F, you give E and say, if I just play this once again, and then I give some more height because I want some more time to come in. So let's give a height of like 10,000 or something. And then you'll see that it gives you in scientific notation. So it's 4.518. So this is like 3 decimal places times 10 to the power of 1. So it's like 45.18 seconds. So you can also get things in scientific notation by changing F to E.
Yes. And what if I want to display more than one variable, say along with the time taken, if I want to display the value of height as well, then do I
Yes.
need
So
comma inside the curly brackets or what?
yeah, you can just keep on typing like this for a height of, say, height of whatever the user have given, say, height from user, and this say also in till 1 decimal place, say, and meters, right? And then let's play this once again, and let's just give you something like this. I mean, you can also give whatever. And so this gives you some output like this. Yeah.
Yes, yes.
So in that way, it's like very straightforward, like how if you want to give multiple variables, all the variables need to be in this curly braces. That's it. So this is one requirement, and the other requirement is this F. So before you start your string, you have to give it F. So this indicates Python that these are F string. F strings are this special type of strings where you can use curly braces. Great. Okay. So now let's go to the second question. If I think there are not many doubt in here. It says the altitude of a satellite. So again, this question is like a satellite is to be launched into a circular orbit around the Earth so that it orbits the planet once every t seconds, right? And then write a program that asks the user to enter the desired time and then brings out the correct altitude of the satellite. So again, and I will, since this is an audience which has not much of a background in physics, so I'll not going to go into the details of how you get it, but just give you the formula in here where, so this is again comes from just a simple Newtonian dynamics where you say that the force of the gravitational force due to the Earth should balance the centrifugal force or the centripetal force on the satellite, right? And if you balance the two, the gravitational force and the centripetal force, you'll get to get the height of the orbit around which the Earth is revolving. Okay, so for that, what you need is something like this G times M. I'm going to explain what these means, and then 4 times pi. So this is for pi, and this to the power of 1/3. And then t to the power, sorry, this is Python, 2/3. Yes. And this is the height from the center of the Earth. So, okay, so first let me explain this. So G is the gravitational constant. So this is the constant for Newton's universal law of gravitation. M is the mass of the Earth. 4 pi is just a factor which comes in. And this entire prefactor has a power of 1/3. And then T is the time of your orbit. So this is the time taken for the orbit to move around. And then 2/3 is the power. So this is actually also related to Kepler's. Okay, there is a times which I missed in here. This is also related to Kepler's laws, which says that your square of the time period of revolution is proportional to the cube of the circular orbit, the radius of the circular orbit. Okay, so this is the distance from the center of the Earth to your orbit. So if you want to know the height from the surface of the Earth, you just have to from this, just have to subtract the radius of the Earth, right? Because this is from the center to the satellite, then from the surface to the satellite is minus of the size of the Earth. So this is the formula which we will be using. And again, we will be using function to put this formula into a way which can be called again and again by the user with different parameters. Okay, so let me go back in here and find out the value of the Newton's gravitational constant. So let's just start here, Newton's gravitational constant, and let me get the value. Yes, so this is the value of Newton's gravitational constant. So I'll just copy this, and this is in SI units. So keep in mind then the other things that we will also be getting in SI. Okay, so let's go back in here and put the value of Newton's gravitational constant. And I think it is, the power is minus 11 as far as I can remember. Let me see. Yes, 6.674 times 10 to the minus 11. There's a 3 in here as well. Okay, so this is this G in SI units. And then again, since there is pi, we are using we can also use numpy instead of just directly writing it, import numpy as np, and then numpy already gives you the value of pi, but you can also give it 3.1416, doesn't matter. And then the other thing that we will need is the radius of the Earth. So let's see, again, Google is our friend, so we'll Google it for the radius of the Earth. For this, and let's see, it is this much kilometers. Okay, so we'll take this in, put RE equals, get rid of the comma. So this is kilometers. So to convert this to meters, we will just add a plus 0, sorry, 3 to it, right? So this is in meters radius of Earth, right? And now we are going to again make a function which will call it, which we will give the height from surface, right? And the user is going to give you the time period of the satellite, right? So we'll call this time period T and tab. So this is it. And then again, we can also, if you want, give the type specifiers. This is again, as I said, it's completely optional. You may or may not give. It completely depends on you, right? And there's some error in here. So yes. Oh, so I missed the mass of Earth. Okay. So the other thing. Earth in kg. Right. Let's call this ME just to be ambiguous. And here I will also write it ME. Right. So the Newton's, so we use the Earth's radius, Earth's mass, and then Newton's gravitational constant. So this is fine. Okay. So now we are going to just return H. So this is just going to return the height. And now this is just like the previous problem where we have used the same thing. So now let's say we give time is equals to in, so this is again float because we want to convert this to float, and then under the float we will give an input and we'll give enter time period in seconds. Right, so this is what we are going to take in from the user, and since we have got the time already, so we will just give the height. So satellite height equals to, now we'll call this height from surface with this time, and we are going to get it in meters because every like this is in meters and this height will also come in meters. So if you want to give it in, say, let's see, we can print this out. So now if I want to get this in, say, kilometers, which is generally what, because this is a very large number, generally speaking, so we can just divide it by 1,000, right? And we can just, for comments, we can just give this, that this is in kilometers. So, okay. So let's say this is an F string, and we'll say the height of the satellite is set height, and then again what we can do is just give something like a 0.2 kilometers, right? So I think this is what we want to do. So just to clear this terminal, what you can do is just give a percentage clear, so this just clears the screen, and now we are going to just start this. So enter the time period in seconds. So let's say we are going to have something like, so let's stop this for a while. Let me clear this. Say we are going for orbit, which orbits say in 2 days. So then we will do 2 times 24 hours times 60 minutes times 60 seconds, right? So this is kind of the number of seconds with which we are going to do it, just for the demonstration. So we are going to put this number in, and then it shows that this is the height of the satellite, which is 9.18 times 10 to the 4 kilometers. So this E is basically 10 to the power of something. So 9.18 times 10 to the 4 kilometers. So I've used the scientific notation in here just because the numbers that come out is very large. And then it's the compact way of writing it. Otherwise, you'll have a lot of zeros which comes in. So is this clear?
So what's the meaning of 1/3 dot here and similarly 2/3 dot here?
Yes, yes. So what happens is Python is quite, I mean, these days Python is quite, I would say that smart. So if you give something like a 1 by say 3, it gives you 0.33333. But what used to happen, so this comes from my earlier days and also in writing codes in C, that this 1 and 3 are actually, to speak strictly, are integers. So then what would happen is that if you want to get just give 1 by 3, then the result usually previously used to come as integers. So if the result is also an integer and not a floating point number, you used to get 0. So just to tell Python or the programming language that this is not an integer, but this is like a floating point number. So 3 dot and 3.0 are same. So yeah, so that's why I've given a dot, but just to be safe and say that this is a floating point number. So this was used to be a problem previously, but now Python is pretty intelligent, and now it can just, if you give a 1 by 3, just given doesn't give you 0, but gives you something like a 0.33333.
Okay.
Yeah, but this is still, for example, if you are writing code in C, then if still now, if you just give a 1/3, you generally get something called 0, because 1 and 3 are just integer numbers, and the output is then also an integer and not a float.
Yes, but then probably we do have floating point divisions and then integer point divisions. So if I just write 1/3, then I mean I should get the floating point number on, not the integer one.
Yes, but I mean, how C works is it looks for, like, your divide is an operand, right? And then it looks for the data types of the numbers that go on the two sides of your operand. And if the data type is integer, then it automatically gives a result which is an integer. And since 0.333 cannot be considered as an integer, it gives you 0. So then it becomes a problem, actually.
Okay. Yes.
But for Python, since it is quite flexible in terms of data types, so it is not so strict, like whatever data type you give, the same data type you have to get out. So it's not strict in terms of what data types. That's why even if you give 1/3, it just works in Python. But just to make this distinction, that even accidentally somewhere it doesn't give you something which is not unexpected, it's just customary and just came up that people over the time, programmers just give this dot. Yeah.
Yes. Yes.
Okay. So other than this, is everything clear in this part?
Yes, assuming that this equation is given and this
Yeah,
program
yeah.
is fine.
Yeah, let's not go into the details of how this equation comes, because I don't want to be, this is more sort of like a computational course. So I don't want to go into the details of the physics of these, which is not the aim of this course.
Yes.
Okay, so then it says that use your program to calculate altitudes of satellites that orbit the Earth once a day, the so-called geosynchronous satellites, once every 90 days and once every 45 minutes. So this is straightforward, just like I did for 2 days. You can also try this yourself. I'll leave it up to you to just do something like once every 90 minutes or once every 45 minutes. It's just very straightforward. Then the last question is not, I would say, a computational sort of a thing, but it's just a question which is related to something called sidereal time and the real time. And this has more to do with physics, or rather, I would say geometry. So what happens in here is that and it says that the time period of rotation is just not 24 hours exactly, but 23.93 hours. It's a little bit smaller for the satellite to complete one orbit. And the reason for this is that as the Earth is revolving, it is also rotating. And it is this rotation which makes the Earth uh, ever so slightly not the same point. So the idea here is that, say, if you have some point in the sky and the Earth rotates and completes a 360-degree motion about its axis, then that same object which was there at some point in the sky returns to its same position. But by the time the Earth has completed a 360-degree rotation, it is also revolving around the sun. It has also moved a little bit in its orbit, which it completes in a year. So because of that small motion of the Earth in its orbit around the sun, as well as its own rotation, it takes a little less time for the same object to come and back to its own position, because the Earth has also moved a little bit. So that small thing is this, I think it's around this 23.93. So it's not exactly 24 and gives you this small thing. So if you want to have a satellite which is fixed with respect to the Earth, so it doesn't move, so then it must have a time period which is not 24 hours, but rather 23.93 hours. Just a small thing in here. So I don't want to get into the details of how this 23.93 comes, but if you are interested, then I will just post this working out of how you can exactly get this in the notes in the channel. Okay. So now let's move on to the next question. which is write a program to ask the user for Cartesian coordinates x and y of a point in two-dimensional space and calculate and print the corresponding polar coordinates and the angle theta in degrees. So this is an interesting question. This is just a conversion from Cartesian to polar coordinates. So let's do that. So I'll then again get rid of these, but just keep this numpy because this is quite a handy module to have, as you have already seen. I'm using quite a different numpy function. So we'll keep on using that. And now what this wants is that it will give you, what you want is values in x and y. And from there, you want the conversion from Cartesian to spherical or polar coordinates. So the way this works is, let me see if I can get a good picture. Yeah. So I think this is a nice demonstration in here is that, oh, not this, I don't want a video. Yeah, so this, if you look at this image in here, so this is like a point in space. So this point is going to have, like this is your x and y coordinates. And if this point has x, the value along the horizontally is the x and the value along the vertical is y, then from Pythagorean's theorem, you can say that your r is the square root of x squared plus y squared, while this angle theta, which is the polar angle, is tan inverse of y by x. So your tan theta is y over x. So your theta is tan inverse of y by x. So, but the thing to note in here is that if you give y by x, the value that you will get is either positive or negative. So it will be either in first quadrant or fourth quadrant. So you have to also look for the sign to put this angle in the proper quadrant. So I'll come to this. What do I exactly mean? But let's just first try to code this up. Okay. So let's see. Now we'll again start a function and def to polar. That's what we will call it. And we will take x, which is a float, and y, which is also a float. And this function gives out an output, which is a tuple of two numbers, which is a float and a float. Right. And this is it. And, or rather, I would say, np dot nd array. So we'll use a numpy array for it. So I'll come to it, what I mean by this. Okay. So let me then take the radius is mp dot square root of okay. So now what this gives you is the square root of x squared plus y squared, and this is the square root of this is the same formula, while the theta that you'll get is mp dot. So this is arctan, while there's something called arctan2 as well. So let's just use arctan, but there is something called arctan2, which also you can use. But this is tan inverse of y by x. So now the problem with tan inverse of y by x is that it will either give you something which is positive or something which is negative, right? But now depending on what your x and signs of x and y is, you are going to have something which is either not in first quadrant but in the other quadrants as well. So for example, if your x is if your theta is negative, if your theta is positive, then so it can either be in first quadrant or third quadrant, right? Because we know that in the first quadrant, tan is positive, and also in the third quadrant, tan is positive. So if you just give y by x, it just gives you a value in the first quadrant, but then you have to also look for the sign of your x and y. And if it is such that your y is negative, while your both the x and y are negative, instead of x and y both are positive, then you have to, the angle that you get from tan inverse has to be added with 180 degrees so that you come to the third quadrant, and then you will get the proper value. Otherwise, there will be a problem that you are not, you will be stuck in the first quadrant, which is not the case. Similarly, if you have something, if your tan is negative, then the value that you will, tan inverse will give you is a negative value, which is this angle, which is here. So then this will correspond to only being in the fourth quadrant, but you don't want that. You want something to be either in fourth quadrant or in second quadrant, again, depending on the sign. So if your x is instead of being positive, if your x is negative, then you know that things are in the second quadrant. Then you have to do something like add like a 180 degrees to it so that you go to the second quadrant. So that's a transformation that is needed depending upon the sign that you get, right? So now once you have gotten theta, you have to see that whether this theta is positive or negative, or rather x and y. So if you go something like if theta is less than 0, so you know that the theta is negative, then you know that it should be either, let me go back in here, if your theta is negative, then it is either fourth quadrant or second quadrant. Now you have to check what is the sign of x. Is if the sign of x is positive, then it is in the fourth quadrant. If the sign of x is negative, then it is in the second quadrant. So there will be another if statement in here. If x is less than 0, then what you have to do is, okay, so there is one more thing is in here, that np dot, so we will be also using this because you see the value of tan inverse of y by x is in radians, but we want this to be converted to degrees. So there is a function called rad to deg. What this does is convert something in radians to degrees. So you will get theta in degrees. So just for comment, and therefore what you will, I'm going to do in here is that, so now I know that my x is negative. So if my x is, so let's rather start with the positive one. So if my x is positive, then and my theta is negative, then I know that I am in the fourth quadrant. So if I am in the fourth quadrant, let me go back again to the illustration. Here, if I'm in the fourth quadrant, the theta is this in the counterclockwise direction, but I want to go in the clockwise direction. So what I'll do is I'll add 360 degree to it. So 360 minus this. So I already know minus something which the theta has given me. So I'll add 360 degrees to it. So that takes me, keeps everything positive, and I'm in the fourth quadrant. So I'll do a theta equals to theta plus 360. While if x is negative, right, then I have to add 180 degrees to it, because then going back in here, this angle will be somewhere here, but I know that my x is negative, so this angle has to be 180 degree opposite to it. So here it is. So I'll add 180 degrees to it so that I go to the second quadrant. Okay, now the other thing, the if theta is greater than 0, the other part of the question, get rid of this, yeah. Then we will again do the same thing. We will check if theta is greater than 0, and if x is greater than 0. Actually, so what this would mean is that we are in the first quadrant, because if theta is greater than 0 means the angle is positive. So It's in either first or fourth. Sorry, let's see, first, second, third, 10. Yeah, first and third. So it's either in the first quadrant or in the third quadrant. So if x is greater than 0, then it is in the first quadrant, and if x is less than 0, then this is in the third quadrant, right? So if x is greater than 0, actually you do not need to do anything. So we will just do a pass. So pass means doing nothing, because whatever result we have got, that's the same thing, because it's in the first quadrant. Now, if I do x less than 0, so I go to the third quadrant. So again, I do the same thing, that I add 180 degrees to it. I'll copy this and paste it in here, right? So now that the theta is properly transformed, what I do is I do a return, and I do a numpy, sorry, np dot array, because I just want to return a numpy array, and just gives an array. The array always comes in a box bracket. So I'll just do a radius and theta, right? So this is what I would get in return. Now I'll just take the input from the user. So I'll just do an xval, just like before. Sorry, it is a float, and then input. Similarly, let's take a y thing in here. So this is just the y value. And then after this, I'll just call to polar. I'll just call this result is equals to 2 polar, and this will give as an argument, I will pass xval and yval, right? And then print let's say radius is something in curly brace, which is we know that the 0th element is radius, and theta is theta. Sorry, theta is your result 1, and this, now let's give the type specifier. So this just gives something like, say, 0.2f and 0.2f. Okay, so this is how this would work. So any array in Python, numpy array being one of them, starts with 0 count. So this is the first element is 0 and the second element is 1. So the result that we have, the first element is radius, so this gives result 0, and the second element is theta, so this is result 1. Okay, so this is how this would work. So let's try to test the code. Create the thing, and we will be now trying different values just to see if things are working fine or not. So let's say x is 1 and y is 1. So we know that this is 45 degrees. So it's 1 and 1. And then your radius is √2, which is around 1.4. So let's give the x coordinate as 1, y coordinate as 1. So yeah, you see that the radius is around 1.141, which is close to √2, and your theta is 45 degrees. So now we will again try the same thing. But now let's just, instead of having 1, I'll put in -1, but keep y 1. So now we are going to the second quadrant, and we would expect something like 90 plus 45. X is 1 and y has to be positive. So this is not fine. So there is some problem then here, because you see that this is x. This takes me to the fourth quadrant, while ideally your x is negative. and your y is positive, you should be in the second quadrant. So let's see what's wrong in this code and let's try to fix this. Okay. So this will be, so this also brings me something that you can try in Spider, something called breakpoints, where you can see how the variables are changing. This is also pretty useful while debugging the code. So let me first clear these variables and put a breakpoint in here. So to go to and breakpoints, you just go to the line which you think is the important line where you can check things. So for example, important line for me is in here where I can check things. And then I do something called here, which is called debugging the file. So I debug the code, right? So this, what this allows me to do is the code halts here. As the code runs and it comes this line, this halts, and then I can like play one line at a time and see how the variables are changing. So this helps me debug the code, right? So I'd give x equals to, so what did I give previously? -1, I guess, which created the problem. Yes. So I give x equals to -1 and y equals to 1, right? And hit enter. So I can, as you can see, I can see what are the different values that have come up. So you see that the theta has come up to be -45, right? So now I have to decide whether the theta is in the first quadrant or in the fourth quadrant. So to decide that, what I do is I come in here, and so if x is greater than 0, then I say that it is in the first quadrant, and then so the theta is negative. So it is coming in here. So it is in the sorry, if theta is negative, then it is either in the second quadrant or in the line 10, second or fourth, right? So this has to be, if x is greater than 0, then it has to be in the fourth quadrant, right? Which it will not be satisfied. And then otherwise it has to be in the second quadrant. So go to the second quadrant. All you need to do is come in here and add 180 to it. So it previously it was 45. So adding 180, it gives me 135. So now if theta is greater than 0, that is not satisfied in here. Oh, got it. So I had to return this. This thing has to be returned every time. After this is done, this has to be returned. After this is done, this has to be returned, because yeah, otherwise it again will is getting changed. So yeah, the problem was once theta was changed, then again this check was again changing it. So as soon as I get the change done, I return this, because it is done, completed. Okay, so now I'll just stop the code for debugging and clear the thing, and let's check it. So you give it -1 and 1. Now this is coming out fine. This is in the second quadrant. Similarly, let's now go and try to see if we get that thing right when we are in the third quadrant or not. So in third quadrant, what we will have is x and y both will be negative, and we will again hit enter. So yeah, this is 225. So definitely we are in the third quadrant. And then the last thing is where both where my x is again positive, while the y is here now negative. And let's see, yes, now we are in the fourth quadrant. So this is now working fine. So is this clear? Like part of the code, I can go through in some parts where this might not be clear. So please feel free to ask.
Yeah, so what's the purpose of an ND array?
Yeah, so what I wanted to return is these are numpy arrays. So numpy arrays is comes from the part a class called ND array. So this is the data type. The data type of a numpy array is an ND array.
Okay. And can you show the use of the breaking point again? I mean, how do you debug the things?
Sorry, I couldn't follow you. Can you please repeat once again?
So can you show the use of the breaking point again and how do you debug the code?
Yes, sure. I can go through that once again. So what you do in here is here you come to the variable explorer, and here there is a button that you can see in here which allows you to just uh, clear all the memory. So all the memory of all the previous thing will gets cleared out. And then what you do is you go in here, you can see the line numbers. You take your cursor close to the line number and give a breakpoint somewhere where you want the code to stop. Like as soon as this line comes, the code is going to halt and wait for you to say that, okay, now proceed to the next line. So for example, say it is line number 13 where I wanted the code to stop because after the checks start. So what I do is I go to this line number, close to this line number, and click in here. So you can see there is a red dot that comes in. This is called a breakpoint. If you click here again, then the breakpoint is removed. And then again I click it. And now once you do this, you'll see an option called debug file. Okay, so I hit, okay, let me also clear this screen just for the clarity. And now once I hit debug file, the code starts. And now you can see this line is highlighted because the code is in, I mean, and here also you can see there is this red thing, which means that the code is running. It's not stopped. And this highlight is nothing, just where the cursor is. But since this is just a stop sign, the code is still running and this has not yet encountered anything. It is in the running state. So what I do is here it says that enter X coordinate. So now it asks for the user value. So let's give it 1 and 1. And now you can see there is a blue arrow in here just behind red. So again, we can get rid of the checkpoint just to show you what's happening. Okay. So now this shows tells you that the code is in here, which is in line 13. And here also you can see that it's marks here as well that the code is waiting for you in line 13. And once the code is here in line 13, there is something called this one, which is run the current line. So it just runs the current line, or which means that it executes this. So here you can see the variables which got created. Here there is a radius variable which got created from line 12. Then there is x, which is passed to this function, and y, which is also passed to this function. And there is this x val and y val, which was input by the user. So these are the variables that are already been created. Now, when I run this, you'll see that there is another variable, theta, which will get created. So let me run this line. And here you can see this again now comes up this theta variable, which got created, right? But now the code is in here, and now it's waiting for the user to see what's happening. So as I was debugging through the code, I was seeing what's happening. So now since theta is less than, now you can see that theta is not less than 0. So this if statement will be false, and now it goes directly to 21, line number 21. And here now theta is greater than 0. So if statement is true, it goes in, and now it checks for x. So x is greater than 0. So it says, okay, fair enough, I am here. And now it goes to line 23, where it just returns radius and theta. And once you do this, it's still here because it's a return statement. You have to run it twice for the return, and then you come back. So here you have come back and you see that the result is here. And once you come out of the function, whatever variables which were part of the function, radius, theta, x, y, all get lost because they were part of the function and now you're outside the function. So you have no longer access to those variables. So now the variables that you have access to are x val, y val, and result, which is this numpy array. You can also double click on this. It shows you the 0th element is this and first element is this. And you can close it in here. And then this is the print statement, which is obviously you can print. And now at any point of time, if you want to stop the debugging, what you can do is there is this stop thing that you can see in here. You just give stop, so the debugging stops. So this is roughly the thing that happens.
Yes, yes, clear. Thank you so much. And I have a small related issue that so there is another session. I mean, session of another course optimization in Python is going to
Hmm.
start at 8:30. So is it possible for you to slightly shift this class half an hour before, say 8:30 in the morning, 8:30 to 10:30, so that I can
Uh-huh.
attend the
Yeah,
class?
yeah, that's totally fine for me because actually for me it's uh, the class starts at 9:30 at night. So for me it's totally fine. Okay.
Then it would be great because I'll have to attend that second because that class is also starting today and I'm interested in optimization.
Yeah, yeah. So that is totally fine. I hope if there are other people joining in, they don't have a problem. I'll just post this in, and then this is totally fine for me. Not an issue. As anyways, I'm starting at 9:30 at night, so there's an 11 and a half hours of time difference from here. So yeah, I can start early.
Sure, thank you. And would you be providing the recording of this of the remaining half an hour?
Yes, yes, yes. So I will share the links. So I will put this like as soon as the class ends, like in 1 or 2 days, I'll be uploading this on YouTube. So you'll have the link to the video.
Thank you so much.
Okay, so but for today, let's stick to the time because I didn't know, but from next time we can start at 8:30. Is that okay?
Sure, I'll have to leave now because I need to attend it.
Sure, sure, sure. Then you can also catch up in the videos that I share, and then you can, if you have doubts, then you can also ask while when the next class starts. So not an issue.
Thank you so much.
Okay. So we are going to then the fourth question in here. Let's see. It says a spaceship travels from Earth in a straight line at relativistic speed v to another planet x light years away. Write a program to ask the user for the value x and speed v as a fraction of the speed of light, and then print out the time in years that the spaceship takes to reach the destination. In the rest frame of the observer on Earth, A, as perceived by the passenger on board, use your program to calculate the answers for a planet 10 light years away, where V is some 0.99. So this is something which is a classic special relativistic problem. Again, I am not going into the details of special relativity, but the idea here is that the time which is required, the time which is calculated depends on where the observer is. So if the observer is on the spaceship, then the time is slow for the observer inside the spaceship compared to the observer who is outside the spaceship. So, and the amount by which the time is slowed inside a moving object for an observer who is part of that moving object or who is fixed to that moving object depends on something called the Lorentz factor or gamma. And the Lorentz factor is, if you look at gamma, it's 1 by, so let's again, just for the same reason, np dot sqrt 1 minus v by c whole square, right? So this is the Lorentz factor. So it's 1 by square root of 1 minus v by c whole square. So if the time outside the spaceship is t, then the time inside the spaceship is t over gamma, right? So yes. So if you're, I mean, for example, let's take an example of Earth and the spaceship. So time on Earth is equals to gamma times time on the ship, right? So this is the special relativistic relation that one would generally have. And let's now again try to have a function which would put this in. And so therefore we will give a velocity in here. So we'll have a definition again, which is a function f time. So we will have distance in here, and then we will have something like a velocity. And this is again in float. Velocity is also float. And what we are going to give are 2 times. So we will give it in mp dot nd array. This is an array. And then we do this. Okay, so we will give velocity as this. Now c is taken to be 1 because what we will do is velocity is in, we'll do right, velocity is in units of light speed. This is only, this value is only a different from 1 for velocities which are very close to the speed of light. If the velocities are slow, then the factor gamma is very close to 1. And then time on Earth and time on spaceship are almost equal. So that's why uh, we keep the speed of light as 1 and give all velocities in terms of speed of light, so that we have values which are very close to speed of light where we are, where the difference is high. Okay, so let's see. Let's say the time on Earth is simple. It's just, and distance, if the distance is in light years, then the time on Earth will be distance by velocity in years, because velocity is in the speed of light and the distance in light years. So your velocity will be in years. Sorry, your time on Earth will be in years. So now time on ship is gamma. I mean, time on ship is then time on Earth by gamma, right? So that will be this then, divided by gamma. And then we are going to return np dot array. This is time on Earth or time on ship. So now this is then again what we have done previously. So we are going to get the input from the user. So for that, let's take in distance. And let's see, this has to be part of float. And value. Distance in light years. Similarly, we'll take in the velocity in here. This will be in units of light speed. And then let's say they call it result, or rather call it times. So they'll get 2 times in here, and we will, let's call it journey time. So we are going to call journey time with the distance and velocity. So once we have got this, we are going to test with let's say restroom of the observer person on board the ship. Okay, so we give a couple of print statements. Time on Earth is times 0.2f years. So this times are in years. Similarly, I'm going to just print this. This is on ship. This is just going to be times 1. Okay, so now we are going to test this problem. Let's start with this. So this is distance in light years. So let's see what the question says. So he says they're 10 light years away. So distance is just 10. And the velocity is 0.99. Okay, so you see here that the time on Earth is 10.10 years, while the time on the ship is 1.42 years. So as you can clearly see that it takes 10 years with respect to someone on Earth for the spaceship to reach the planet, while for the person who is on the ship, it has only taken 1.42 years. So like 1.5 years. So this is also related to this sci-fi stuffs of time travel where people are aging differently. All these things come from these special relativistic concepts. So this is a classic example of what's happening in here. So is this clear to everyone?
Yeah, yeah, it's clear.
Okay, okay. Then I can just simply move on to the next question. I think this is probably the last or the second last questions given the time that has been, and then we'll continue from the next class again from where we left off. Okay, this is a quantum potential well problem. So let's first read the question. It says that a well-known quantum mechanics problem involves a particle of mass m that encounters a one-dimensional potential step like this. So there you can see the figure in here. So actually, let me go and open up the, yeah, this is question 5. Yeah, a well-known quantum mechanics problems uh, involves a particle of mass m that encounters one-dimensional potential step like this. The particle with the initial kinetic energy E and a wave vector k1 enters from the left and encounters a sudden jump in the potential energy of height v at position x equals 0. By solving the Schrodinger's equation, one can show that when energy E is greater than the potential V, the particle may either A pass the step, in which case it has a lower kinetic energy of E minus V, on the other side, and a correspondingly smaller wave vector K2, which is square root of 2m times E minus V over h bar, or it may be reflected keeping all of its kinetic energy and an unchanged wave vector but moving in the opposite direction. Suppose that we have a particle of mass m to the electron mass, particle with mass equal to the electron mass m, which is given this, and the energy of 10 electron volts encountering a potential of height 9 electron volts. Write a Python program to compute it and print out the transmission and reflection probabilities. Okay. So again, I'll not go into the details of quantum mechanics, but this is also related to something called quantum tunneling and uh, particle reflections. So the idea here is that you can think of in quantum mechanics the particles as waves. So normally, if you think about like waves in a swimming pool, for example, you see the waves on surface waves on the water, and if there is a bump somewhere, then what happens is that part of the wave flows above that bump, depending on the size of the bump. If the wave is having a lot of energy and flows like a very strong wave, then part of it is reflected by the bump, while part of the wave flows over the bump and goes to the other side. So this is and a classic example of this. This V is the size of your potential. So this is kind of, you can think of as the barrier to which the wave is encountering. And if the wave is having an energy more than that of V, then the wave that goes to the part of the wave that goes to the other side gets an energy of E minus V, while the part of the wave that gets reflected gets the rest of the energy and gets reflected back. Okay, but the wave length of the waves change, and that depends on this energy difference. So the wave which gets transmitted, which is T in here, has a wavelength k2 with like a wave vector k2, while the wave which is coming in has a k1, and while it goes back, it has the same thing, like a same wave vector. Value of the wave vector is the same. It just gets reflected if you think about it. Okay, so there are the reflection and transmission probabilities, which comes from solving this Schrodinger equation, which again, I will not go into the details of it. I'll just give the formula of what's the amount of which the waves get transmitted and the part of which the wave gets reflected. So it turns out the reflection probability, which is called R, is again, there will be K1 minus K2 divided by, oops, K1 plus K2. This has to be squared. This whole square. So this is the reflection probability. Similarly, if the wave gets transmitted, the transmission probability is just, let me just copy this. The denominator remains the same, but the numerator is just, sorry, I squared. This whole squared, and similarly, a denominator is then again K1 plus K2 whole square, while your numerator is 4 times K1 times K2. So this is your transmission probability. And one thing to note in here is that if you add the two, like R plus T, this is equals to 1, because these are probabilities, and there are only two probabilities of things getting either reflected or transmitted. So if you add the two, this should give you 1, and this is exactly what happens in here. Okay, so now we have to define what this K1 and K2 are, right? So this is already given in the question as well. So K1 is just square root of, so this is 2me over h bar, right? So let's see, 2 star e. This is square root of 2me over h bar, whereas K2 square root of minus V H bar. So these are the three things. And now let's wrap this in a function. This will be def, let me call it quantum probabilities, the quant prob, right? So what are the things that we will need? We will need the mass, which is obviously a float. We need the energy of the particle, which is again a float. And we need the size of the potential, which is again a float, right? And what we will get is an np dot nd array, because it is the array that we are going to get. So we put this in, right? And let's first then define this, and then they should have to return array. It will return R and T. These are the two things that we are going to return. So now we have to define the mass of it, of an electron, right? So let's do these. Me equals so, and what more do we need? We need an electron volt. Okay, this E is in SI, so but the value of E is given in electron volt, so we have to find out what is the amount in electron volts. So electron volt to SI, and this will be in joules. So you see, 1 electron volt is 1.6 times 10 to the 19 joules. So we'll just take this in. Okay. So E is this minus 19, right? And let's see what's missing in here, H bar. So H bar is like a quantum mechanical constant, the Planck's constant. So let's see. So H bar is nothing but H by 2 pi, basically. So let's write this back, go back, and do H bar equals to E, I think it's minus 34. Yeah, minus 34 divided by so the definition of H bar is H over 2 pi. H is a Planck's constant. So this is H bar. So we get this. And now we'll just put in the value of the user. So we'll also put in this ME as well. So ME is this electron mass, which is 9.11 times 10 minus 31. 31. This is in kg. Right. This is in joules. And this is in SI. SI. The unit is complicated, but we know this is SI. Okay. So now then we will go in here and just put in the values in there here, just like before. So what are the values do we need? We need mass, which is here. Then let's do a float. And inside float, we'll give an input. And the value mass in electron mass. So it is in electron mass that we want the mass to be put in. Okay, so we need then energy E and the potential hot. So energy in electron volts and the potential also in electron volts. So this is in ME, so we just multiply ME, sorry, we just to multiply ME to it, we just multiply EV to it. Let's call this EV. So we multiply EV to it. So this is in electron volts, gets converted to electron volts, and similarly EV. So everything is now in SI units. And then we go and type probs. So the probabilities equals to quant prob ME, and instead of V, this will be potential that we are going to call it by. And this is mass, right? And then we do a print f string, we do trans, what did it R, okay, reflection, we do robs 0.2f, so this gives me the reflection probability, and similarly transmission negative robs 0.2f, right? So the first one is reflection and the second one is transmission. So that's how it is. So let's give it in here. So the mass in ME, so it says that the same as the mass, and oh, sorry, I have not changed the prompt. Energy and then potential height. So let's stop this, clear this terminal, and let's run this again. So mass is 1 electron, mass of an electron. It says the energy is 10 electron volts. So the energy is 10 electron volts, and the height of the potential is 9 electron volts. So yeah, so now you see reflection is 0.27. That is the probability of things getting reflected, while the things getting transmitted is 0.73. Since the energy is pretty high compared to the potential height, there is a quite a significant fraction or probability of stuffs getting transmitted, particles, right? So is this clear? Please let me know if there is any
Yes, sir.
doubt.
Yes.
Okay. So then let me just move on to the last question of today. This will be more sort of using lots of equations and from this Keplerian mechanics, just to sum this up. And I think this is also a nice place where we end today's session, because from the next session, we will be discussing more about iterations in Catalan numbers, something which is a little bit different. This was all about using different functions, from starting from very simple functions to something which is a little bit complicated. So let's do the last questions for today's session. So let's then get rid of these. Okay. And let's see the last question of planetary orbits. Okay. Let's see what they say. Planetary orbits. The orbit in space of one body around another, such as a planet around the sun, need not be circular. in general, it takes the form of an ellipse with the body sometimes closer in and sometimes further out. If you are given the distance L1 of the closest approach that a planet makes to the sun, also called its perihelion, and its linear velocity v1 at perihelion, then any other property of the orbit can be calculated from these two. Kepler's second law tells us that the distance L2 and the velocity v2 of the planet at most distant point or aphelion satisfy L2 times v2 equals to L1 times v1. So this is actually something related to conservation of angular momentum. But let's not get into the details of these. Write a program that asks the user to enter the distance to the sun and velocity at perihelion, then calculates and prints the quantities L2, V2, orbital period T, and orbital eccentricity E. Test your program having it to calculate the properties of orbits for the Earth, for which L1 is this, V1 is this, and the Halley's Comet, for which L1 is this and V1 is this. Among other things, you should find that the orbital period of the Earth is 1 year and that of Halley's Comet is about 76 years. So let's try to do this. This will be using a bunch of different formulas, all related to orbital mechanics. Yeah, where you assume that the trajectory of an orbit of a two-body problem. So there are two bodies, one each revolving around each other due to the force of gravitational attraction between them, and then that gives you a general solution, which is an ellipse, and then there are relations which exist. So I'll come to these relations one at a time. Okay, so let's see. So there is this L1, which is the perihelion, and then there's L2, which is the aphelion. So perihelion is the closest point. So the sun and the earth are closest to each other at perihelion, while they are farthest away from each other at aphelion. So let me write down the formulas in here. So L max, right? So L max is the perihelion thing. So let's see what are the things that are given. Given things are L mean and V max. Okay. So what are given are L mean that the user will enter and V max. So remember one thing in here is that when since this is L2 times V2 is L1 times V1, so then that would mean is that, say, take an example, is 2 times 3 equals to 3 times 2. So both gives you 6, right? So when L is the smallest, then V is the largest. And similarly, when V is small, L is the large. So L max is when you are at aphelion, so you are farthest away from the sun, then you are moving very slowly because then it is V mean. So V mean will go with L max, and similarly L max, L mean will go with V max. So when you are closest to the sun, then you are moving at the highest speed. So that will make it 3 times 2 equals to 2 times 3. Just an example so that you understand this. Okay, so the quantities at perihelion is given. So if it's perihelion, then that would mean L is L mean because that is closest, and then V has to be V max. That's the highest velocity. But given these two, we are which the user will input, we are going to find out what are the other things that we have to calculate, the orbital parameters. So let's see the relations. So given these, the other is very simple. So then if you want to find out V mean, then this will be V mean is equals to, let's first find out V max and L min. Okay. Eccentricity. And then there are these formulas for C. Okay, so there is a constant called C. It's an important orbital parameter, so which is dependent on V max and L min. So this is something V max times L min whole square by G times M. So m is the mass of the sun, right? So let's call it m sun, right? So Vmax times L mean whole square divided by Gm, where m is the mass of your sun, right? And so once you know C, with the help of C, you can get to other orbital parameters. So which we will get to in a while. So let's also write the orbital eccentricity here. The orbital eccentricity is Vmax times L mean divided by G times M sun minus 1. So this is the formula for eccentricity of an orbit. So eccentricity tells you how much elliptical an orbit is. For example, I mean, if your major axis and minor axis are all zero, all the same, then you have a circle, and then you have an eccentricity which is equals to 0. Okay, so now you have C, you have the eccentricity, which is Vmax times L mean over Gm minus 1, and then now you can find out Lmax, which is the distance of the to aphelion. Then that would be okay. Then we can take this Vmax times L mean whole square divided by G times M times 1 minus ECC. So this is the eccentricity. So this gives you Lmax. This is the distance of the aphelion, and then the velocity at aphelion is then becomes pretty straightforward because the product of Vmax times L mean should be equals to V mean times Lmax. So that would be Vmax times L mean. So this entire thing divided by Lmax. Great. So we have got all that we needed, and then we want to also find out the time period. For finding out the time period, we need to know the size of the semi-major axis. Turns out the size of the semi-major axis is C over 1 minus A's ECC square. This is the time of the major axis. Sorry, size of the major axis. Then the time period of revolution is square root of, so you want the square root of 4 pi square over gm times a cube. Okay, so it's 4 times pi square divided by gm, g times m sun times a star star 3, right? So this gives you the time period, right? So now we have to also get hold of the constants that we have in here. The constants, let's for now figure out the, see, figure out the constants in here. We'll uncomment that later. So the one of the constant is G, which was we have got previously, the Newton's gravitational constant, while the other will be M sun. So let's take this. So this we have already gotten. E minus 11. Y, sorry, my bad. This is in SI and Emson. Solar mass kg. Okay, so this is the solar mass that we have. So let's go and put this in. Right. So now def orbital. Let's see, test your program to calculate L2, V2, T, and okay. So orbital params is, let's call this function orbital params. And for this, the input will be L mean, B max. And both of these will bring float. So you have a floating point number of L mean and a float of V max. And then you'll get NP dot ND array here. And then okay. So now let's see. This M is M sun. Okay. So now we are going to return the different orbital parameters. Let's see. We'll do np.array and the first one. Let's see what are the first quantities. So it first for L max, V mean, followed by time, and then the last one is eccentricity. Right. This is what we get. So now we'll just float this in, float just like before, input, enter velocity at okay, so perihelion is given, right? Velocity at enter distance, enter perihelion distance in meters. Yes. And then similarly float input entered perihelion velocity in meters per second. These are the two things that we will put in, and then orbit is equals to, we will call orbital params. And the values will pass. So we'll pass L min and V max is what we are going to pass. And now we can print the stuff out. Print we are going to print, let's print it in the same order that we have got. So aphelion distance equals to or with 0 colon point to E. This will be in meters, right? So there are 4 quantities. So we'll have 4 print statements and just change the thing. So similarly, aphelion distance, then aphelion velocity in this much meters per second, orbital time period. So this is 1, this is 2. So we want the time period to be in years. So they will divide it by a year, right? And we will define a year in here. 1 year is in SI units. It's 365 days times 24 hours times 60 minutes times 60 seconds. So this is a year in here. So we have this many years. And then the last one is eccentricity. Eccentricity and 0, 1, 2, 3. And this would be, say, 0.3 F. Okay, so I think we are now ready for this. So let's run this program. So enter and let's test the 2 things that are given in here. So the first one is for Earth. So for Earth, we know that the distance of a revolution, orbital time period should be roughly 1 year, and the orbital eccentricity will be pretty low. It will be pretty close to 0 because the Earth's orbit is almost circular. So let's see if that comes out. 1.47, 0, E11, distance in meters, velocity 3.087, 0287, 3.0287, 287, E4. Yep. So let's see. So I think we are off by some points. So let's see where we have gone wrong by in here. This is in meters per second. The aphelion velocity is okay. Time period is not right. Should be year. So let's see. 0, 1, 2, 3. And eccentricity is also not coming out to be right. So Vmax times L mean by G times M sun. Okay, so let me check the formulas, which is just a problem with some formulas which I have entered most likely. So let me check the formulas for question 6 that we have done in here. So I have the correct formulas in here. Let me just check it, what I have made wrong in it. Oh, Vmax squared times I mean, okay. So I think, yes, there's the problem, I guess, is this thing, this expression. And I think I have used something Vmax squared times L mean. Whereas I think in eccentricity, I have missed the square. So maybe this is the only problem. Let's see. Let's see the other problem, if there are other stuffs where I've made any mistakes in the formula. And then C is whole square by GM sun. So let's just test it with this. Okay, I have to again put in the values. So L1 is 1.47, 0 E11, and the velocity at perihelion, this will be 3.0287, 3.0287 E4. Okay. Yes, now you see it's right. The orbital time period is 1 year. The eccentricity is very close to 0. And you can see that this is the distance of the aphelion. So the perihelion distance is this. The aphelion distance is a slightly larger than the perihelion. As you can see, it's 1.52 times 10 to the 11. So this also shows that this is almost circular because the farthest point and the closest point are also close to the sun. And then the aphelion velocity is this, the orbital time period is 1 year, and the eccentricity is 0.016. Okay, so this is the first part, and then let's test it for the Halley's Comet as well. I think now I'm pretty confident this is going to give you the right result. So for Halley's Comet, it's 8.7830, 7830 E10, 0.7830 E10 is the distance to the Halley's Comet at perihelion, and then the velocity is 5.4529 E4. Yes, so you can see it's around 76 years. It's 75.9, so it's around 76 years that you see the Halley's Comet. Add your distance to your orbital eccentricity is 0.967, so it's extremely eccentric compared to the Earth, which orbital eccentricity was very close to 0. Here, orbital eccentricity is very close to 1. So it's a highly eccentric orbit, as you can see. So it's extremely elliptical. And you can also see that the distance to perihelion is 8 times 10 to the power of 10, roughly speaking, or 10 to the 11, whereas aphelion distance is 5.27 12. So from 10 to the 11, roughly speaking, you go to 10 to the power 12, or rather I would say 10 to the 13, it's 5. So it's extremely elliptical orbit. So I think we are at the end of what we have covered today. So are there any questions or doubt? Is there any question or doubt?
No, it's clear.
Okay, great. Then I hope that this was beneficial to you, and this was you have learned some basics of computation, and some basics of Python as well. And now you're comfortable in creating functions and using Python for your own work. So I'll now conclude then today's session, and see you in the next one. Bye.
Thank you. Thank you.